There we go. All right, back. So here's a little section here. What is a computer? Let me talk about the textbook a little bit. The text, which is listed in the syllabus, is basically covers all the material that you need to know. The first 6 chapters. There it is, right there. So it's a great book, and really a very useful book. But actually, if you already have a textbook from, say, another course that you took, maybe at a community college or whatever, you can use the other book, because all these books are very similar. They have to cover the same thing. They're all covering the C++ language. There's a seat down here if you want to take a seat. I know it's crowded in here, but this is the last day it's crowded. No, it gets crowded when I give the tests. Then it gets crowded again. So once again, I recommend the book. It's a great book, but I teach the class so it can be standalone without the book. That's because over the years textbooks are very expensive, and I have students who are always asking me if they can use a different book. So I created problem sets and so on that stand on their own, that don't require the book. And but you may need a book to get through the class. But if you already have a book or like a different kind of book, then you can do that. But this is the recommended book. All right, that's the book. And if you look at the book, the first chapter is about what a computer is. And I just jotted some notes here. And I'm going to give you a quick overview about what a computer is and what programming is. And maybe there's some learning in this, I don't know, but I'm going to run through it quickly. The real learning that I think happens in this class is when you sit down and work and try to solve problems. That's where I think the learning content comes in the class here. All right, there's this thing called computer architecture. How is the computer built? How is it designed? Right, so that's a topic called computer architecture. And here, at Cal State San Bernardino, we have courses on computer architecture. In fact, we have a computer engineering major, and in that major they cover a lot of topics in hardware design. Right, so this is hardware design. And basically you've got a CPU, a central processing unit, and this central processing unit executes machine instructions. So that's what a computer is. A computer runs because it's interpreting instructions, and it's the CPU that's reading and executing instructions. And these instructions are stored in RAM, right? So if you have a computer got 8 gigabytes of RAM, right, something like that. That RAM. That's where when a program runs, you've got machine instructions stored in a chunk of RAM, in an area of RAM, and the central processing unit is picking one after another and doing what that instruction says to do. Now these are primitive low-level instructions. They're not like, print high. There's no machine instruction that's to print high on the screen. That's a very high-level concept. There's a very low-level things like machine instructions have to do with, copy, copy 4 bytes. The number stored in 4 bytes at address, 99876, and put it into register register B, and then go to another memory location, copy those bytes into register C, and then add those 2 registers together and put the result in another register, and then copy that back into RAM. That's the low-level kind of machine operations. We're not going to look at those in this class. Other than today. So those are called machine instructions, and that's a topic that's part of computer architecture and computer engineering. So you've got this concept of computer programs. So you've got these computers, the hardware. The hardware is capable of storing information in memory, and it's capable of carrying out instructions, which are also stored in memory. And so these instructions comprise the programs. Computer programs are collections of data and machine instructions that are loaded into memory and executed by the CPU. So let's suppose you have a program, like say a spreadsheet program, right? Microsoft Excel, and the program is a collection of machine instructions and data, which is stored in the disk drive. So it's just sitting there in a disk drive. It's a file, and the file is just this sequence of data, of numbers. And so when you want to launch the program, you double-click the file. Right? That's one way to do it. There's other ways of launching programs. So what happens when you launch the program? What happens is the operating system reads the data that's in the file and copies it into RAM. And then after that copy is done, it sets up, some conditions and some information. The operating system is going to manage the execution of that program. So it copies the data, the instructions and its data into RAM, and then it lets the CPU start loading machine instructions from RAM and do what the instructions represent. So when the program is running, we refer to it as a process. When the program is just sitting there on the disk and it's not running, it's a program. But when you load the program and execute the program, it appears inside this operating system, the running instance of the operating system. It appears as a process. So we have this thing called an operating system. So the operating system is a program. It's a collection of machine instructions and data together, which are sitting on the disk drive. And when you turn the computer on, those machine instructions and data are copied from the disk drive and copied into RAM. And then the CPU starts executing those instructions that were just copied into RAM. So that's a process called booting. So that's built into the hardware. So when you turn the computer on, it's all hardware. There's nothing in RAM. So the hardware has to load the operating system, and it does it in a couple of stages. We're not going to get into that, but that's a topic. That's what's going on under the hood there. And the operating system is the thing that manages everything. So that when you write a program and run a program, you tell the operating system, hey, I want to run this program. The operating system loads the program into RAM, and it directs the CPU to start loading and executing instructions that were copied into RAM. So I've been talking about memory, but what is let's talk a little more about memory. The smallest piece of information in a computer is a bit. And a bit is either on or off. So if it's off, it's a 0. If it's on, it's a 1. It's a yes or a no. An up or a down. Just two states. And so that's a binary digit. A binary digit is just a 0 or a 1. Just like a decimal digit. A decimal digit is a 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So there's 9 decimal digits. Or you can have a hexadecimal digit. There are 16 hexadecimal digits. So when you look at a number that's represented using binary notation, it's going to be a string of zeros and ones. And that's essentially how information is stored in a computer, whether it's on the disk drive, or whether it's in RAM, or in the cache, or in a process, a register, whether it's sent on the internet. It's just a sequence of zeros and ones, ultimately down at the lowest level. And they're represented by voltages and or storage media. They have to represent zeros and ones in some way. And but it's inconvenient, of course, for humans to work with binary representations of numbers. So we usually look at decimal representations. So there's this translation that's done for the purpose of making information more understandable to humans. So if the computer is storing a 1, 1, well, that's a 3, right? Because this one is this is the 1's place, and this is the 2's place, and the next one is the 4's place. Just like in decimal notation, it's the zeros, the tens, the hundreds, the thousands, the 10,000s. So in binary notation, you've got the zeros, the 1s, the 2s, the 4s, the 8s, the 16s, the 32s. Also, it's typical to use hexadecimal notation. It's actually, in some situations, it's more convenient to use hexadecimal notation, even though we're not normally used to using that. And so basically, the hexadecimal digits go from 0 to F. That's 16 different values. I mean, they could have been any character, right? We could have used, a squiggly line and a dash and a period. That doesn't matter. But this is just the convention that we use. We go to 0 to 9, and then we start up at A. That was the convention. Someone just thought of this sometime at one point in the past and said, well, we'll use A to be a 10. And it's just stuck. So you've got these 16 hexadecimal digits, and so your decimal representations of those digits go from 0 to 15. You've got to get used to counting from 0 in this class. Computers start counting from 0. Humans start from 1. You want to count things, how many students are in the class. You go 1, 2, but a computer doesn't do that. A computer goes 0, 1, 2, 3. Oh, 4 students. Usually when you stop your counting, you add 1 to get the number. If you start at 0, you've got to add 1 to the last index. That's what we call it, an index. So you'll see the decimal digits range from 0 to 15. That's 16 different values. And the binary representation, we need 4 binary digits to represent the 16 hexadecimal digits. And that's what they look like right here. And sequences of 8 bits are called bytes. So a byte is 8 bits in a sequence. And let's see, what do I have here? So bytes fall in this range. They start at 0 and they go up to 255. So if you have 8 ones in a row in binary notation, that equals 255. That's a byte. So these are all of the bytes. These are all possible values. So I don't list out, there's 256 different numbers in this range. Remember, start the counting at 0. So this table, which lists every possible byte value, has 256 entries. So I left some of them out. You start here, and then basically, increase by 1 as you go along, and you end up at 255. That's a string of 1s, 8 ones. Hexadecimal notation is FF. And I'm just going to skip over that. So C++, that's the language that we're going to be working in this class. And this language is called a high-level language. So we can do something like we can say, print high. That's one statement in C++. Print high. That's one statement. And that one statement is then translated into several machine instructions and data. But there's a lower level language that's closer to machine instructions. That's called assembly language. Assembly language is it's a convenience. Instead of working directly with machine instructions, which are pure numbers, we just look at the these identifiers that are written in terms of characters and numbers. So like this MOV1, so this is move. That's a move operation. This is hard to see because it's breaking here. Like that. This is a program written in assembly language. This program compiles and runs on Linux computers, but it does not run on other operating systems. That's because assembly language programs are dependent on the operating system. So programs written in assembly language are not portable. But programs written in C++ are portable. You can take source code for a C++ program and build it on, using Xcode on a Macintosh computer, and it will run unchanged, if you write it that way. And you could also build it and run it on Linux or Windows, or iPhone, iOS, or Android. It will all run the same way. And but assembly language is more tied to the operating system, of course the hardware as well. And these are what the instructions look like. And I have a demonstration, but I'm not going to do it. Basically, you create a file, like here, and this say hello.s, that would be a file, and we paste those instructions in there. Oh, by the way, this program, when you run this program, it just says hello. That's what it does on the monitor. And so you would put that program in a file here, and then you would execute a program, which is this AS, right, assembler. So you run the assembler. Assembler is a program, and it will read the file, and it will generate another file here. And it's called object code. It has the extension .o. And then after you, basically this file here has machine instructions in it, but it's not yet ready to run. You have to run it through what's called the linker. That's LD here. So you've got another command. Once you produce say hello.o, you take that result here and you pass it into the linker, this LD command, which is another program that does more processing, and it outputs a file which is now executable. So this file can be loaded by the operating system and run as a process. And we're going to follow a similar procedure in this class to compile C++ programs. We won't do it in 2 steps, so we'll do it in 1 step. One step that we do translates the C++ code into machine instructions, but they're not linked. In other words, they're not yet runnable. It can't find operating system resources yet, and other things. Those machine instructions, the object file is then converted into an executable. But we'll do that in 1 step. So compiling and linking will be done in 1 step. We're going to work in Linux in this class. In the labs, we have Linux computers, so this will give you some experience using another operating system. And it'll give you some experience understanding how to interact with the operating system from what's called the command line. So normally we interact with the operating system through a graphical user interface. Right, so we start the computer, look at our files. The file system is a hierarchy. We've got folders and files in those folders. So this is the graphical user interface of the operating system, and we're interacting with the operating system and programs running by the operating system. We're interacting with them through this graphical user interface, but there's an alternative interface called the command line interface. We could also call it the console interface. And that's where we type in commands. and we issue commands to the operating system, and the operating system then, does what we want. This is how we execute that program that's written in assembly language. See, this is the output from the linker, and we have this / say hello, and that'll run. Then when the program runs, it'll just say hi. That's my overview of what a computer is. Let's take just a brief look here. This is a hello program. This is kind of your starting point in the class. The first thing you'll do is create a file that has this code in it. And this code, and then we'll save that file, and then we'll run the compiler and translate the code into an executable. And then we'll run the executable. This is the command for compiling. So let's suppose we take this text in a text editor, and we create a file with this text in it, and we call the file hello.cpp, and CPP, that's for C++. And then we run the command C++, the command. We type it in on the command line, and this is an argument. This is an argument for the command. So the strings that follow the command on the command line are the arguments for the command. And then this command will launch a program, read the file, and then generate an executable. And by default, it'll name it a.out, and that's a Linux convention, right? On Windows, it'll create a different name, and it will end with .exe. And Macintosh, it'll have a different convention, and they end with a different extension. I don't know what it is on Mac. Can't remember. And that's how we run it. So this is the starting point in the class. So this is a hands-on class. And so most of what we're going to do in here is talking about code and learning how to solve computing problems by writing code. And this will be the starting point. Okay, here's the first thing to think about. The deadline is 2 days from now. So by September 26th, you should complete this lab. And the learning objectives is to learn how to work from the Linux command line, and to learn a simple approach to compile or run console programs written in C++. So that's the purpose of the first lab. Now you can still work at home here. You don't have to come into campus to do this, although I recommend that you do this lab on campus, because I'll be in the lab. Jaron Willis, the teaching assistant for this class, will be in the lab. There may be an additional person in there helping out as well. So usually students are a little bit lost in the beginning, and it's just a matter of practicing a little bit, some basic commands, and getting comfortable with the Linux environment. But you can actually do the exercises at home by logging in remotely into a Linux system. So you can use something called a secure shell program and connect to one of the lab machines, and then you'll see a console window, and you could start typing away and doing the lab that way. So that's also possible. So in order to do the lab, and the lab is, the lab room is JB 359. That's the third floor. There's 30 computers in there. So some of us meet today on Mondays, the others meet on Wednesday. And I'm not too strict about the days. You can come on a different day, is all right. Because you'll see as we go through the class, a lot of people will prefer to work at home. And because you have to work at home anyway. You can't do everything in the lab. You have to do some work at home. So you got to figure out a way. You could come into the labs also. You don't have to work at home. And if you can't get your work done in the lab, you've got an assignment to do, there are open hours in the labs, and you can access the labs to finish your work that way. So JB 358 and JB 359, those are the two labs that you can work in. So you'll have an account. So when you sit down in the lab today, some of you will be in the lab today, and you'll be able to log into the computers, and then I'll guide you through what to do next. All right. And so the purpose of this lab is to just become comfortable with the command line interface. Now, all common operating systems that we use to do work on Linux, OS 10, and Windows, they all have a command line interface, and they're all very similar. So what you learn here, you can take that experience and carry it over to the other operating system environments and do similar things. In particular, the Linux interface is console interface is almost identical to the OS 10 interface, as they're both Unix operating systems. So the commands are similar. And but Windows is not a Unix operating system, so some of the commands are similar, and many of the commands are different. But they all essentially do the same things. You just have to know what the command name is and maybe how to pass in the arguments. And so here's the tutorial. It's an online tutorial. And what I want you to do is basically go through this and practice the commands that are talked about in this tutorial. ls, this is a command. ls displays the contents of a folder. And this is what it looks like on the console window. Let me show you on Windows what that would look like. Okay, so here's the command prompt for Windows. Maybe that's too small, so I'm going to increase the font here. Maybe that's good enough. So ls, command not recognized. Okay, so this is a Unix command. ls will work on OS 10. On Windows, you use dir, and it's similar. It gives a listing of what's in the folder. And then you can move around. You can go cd desktop like that. See that? And look at my prompt. This is Windows, by the way. We're in Windows. C, that's the drive letter, C drive, and then colon slash. This slash, that means that's the root of the folder hierarchy. So folders form a hierarchy. There's the very top folder called the root. Each drive, because each drive has a root folder. And that's why you see a leading slash here. That's the root folder. And then you've got these folders. There's a number of folders under the root, and one of them is called users. And in that users folder, you've got a number of other folders, and one is called Turner. Under Turner, you've got other folders, and one is called desktop. And that's the same thing as doing this. It's like, you know, I'm in this tool called not Internet, it's called Windows Explorer. I don't think people use that term anymore. I don't know what they call this. This is your folders. Right? So this is the graphical user interface tool that you use to look at your folders, to create them, to delete them, to manage files, and so on. So look, this is the contents of the desktop, and we can view this. Let's see if I can change how it's viewed here. I will view details. There we go. Now this is a different kind of listing here. So it shows these things, and these are subfolders. Like here's a folder called 322. Now this is the graphical view, and this is the text view. And if you look in here, if I go dir in the desktop, you'll see that there's the folder right there, 322. So these are two different tools, two different ways of viewing the folders in your system. And you know, in lab and when you do your work, you're going to need to use the console for certain things. But you have a choice. Sometimes you don't have to use the console, then you can use the graphical user interface. You can do your work that way. Like, look at this. I double click into 322 and I see, oh, there's 3 subfolders under 322. How do you do that? What's the corresponding action in the console? Yeah, CD, that's it. CD 322. And then I'll do dir. There it is. Downloads Eclipse and Workspace. Exit. That's the clean way to close the console, by the way, but you can also just hit the X there, right? It's a sloppy way to do it, but it's not a big, it's the same thing. Okay. So, but now on Linux it's going to look differently. Now here, let's see if I'm still in there. Yeah, here I've logged into one of the lab machines. And so I can use ls here. This is my home directory, pwd, print working directory. This is the path in the folder hierarchy in the labs. So actually the lab machines have this old-fashioned shared file system. So every lab computer basically is showing this file system that's stored across the network. It's like a network file system. And there are some local files on each individual computer. It's only stored for that particular computer. But then there's also the files that are common to all computers in the lab, and those are stored in the network file system. And this is the path in there. So I could log into a different computer and I'm going to see the same files. You know, this is my home directory, by the way. It's called Turner. So you'll have a home directory in the labs. And you'll keep your files in there. You'll create subfolders. You'll put things in the folders. That's where you're going to do your work. And then just like that, you know, ls gives a list. As you can see, I have a folder here called CSE 201. I can cd into it. Change directory. I think that's what it means. ls, well, there's nothing in there. I could just cd space ... and go back. Now, I'm logged into this computer remotely, and I only have a console view. I can't start the graphical user interface in this context. I cannot look at my folders of files on that lab computer from here the way I'm doing it right now. I'm restricted to the console. And this is a common situation for system administrators. You've got system administrators that are controlling many computers. And sometimes they're controlling computers that they don't even see, they can't even touch. And that's more and more common. Like, for instance, the cloud computing, they call it, cloud computing. And that you, to configure and control a computer remotely, you're going to use a combination of tools. Sometimes you'll use graphical user interface tools. Sometimes you use console windows. So it's very common for system administrators to use these console windows. So if that's where you're headed in your career, this will be, you know, a good starting point for you in this class. That's some very interesting things, actually. Just let me get off on a tangent a little bit here. Take, for instance, Amazon. Amazon is the biggest provider of cloud computing in the world. And and here's an example. Netflix, 100% of Netflix's computers that are used for serving, videos on the internet, all of them are virtual computers provided by Amazon. Netflix does not maintain their own computer systems for delivering video. They may have computer systems in their office, to do office work, but not for their video delivery system. Those computers are all housed by Amazon. In fact, and those computers are provided as virtual machines. They're not even, you don't even log into, you don't control a machine directly. You control a virtual machine. You're interacting with a program that behaves like a computer. And of course, it's running on a computer. So it's very interesting. There are lots of very interesting things happening in that area, cloud computing. So in this class, maybe you're going to get familiar with some of that terminology and some of the techniques that you might end up using later on in your careers. All right. Let's see. I'm going to get off on another little tangent here, just to show you a little bit about some of the work that we do here at that I'm involved in with other professors and students. We've been working on this video game problem, which is to build a 2D video game called the Kuna Reaver, and we're pretty much done. And it's a free game. It's called the Kuna Reaver, and you can go to this web address. You can download and play the game. And I would appreciate it, actually, if you do that. And if there's any bugs, let me know, because this is labeled a release candidate right here. That means there's nothing left for us to implement. And it runs correctly. We don't see any bugs right now. I know there's bugs in there. So we need people to play the game to break it for us and let us know what's wrong. If you're kind enough to play the game, and it is a fun game, I think it's fun anyway, please send me feedback. Send it to my email. Oh, lost this.